So good evening. So now today we are going to have a discussion on one form of interprocess communication known as pipes. So last week we discussed on the processes and virtual memory. So today the discussion will be on one of the methods of inter-process communication. So what is meant by inter-process communication means communication between different processes. That means sending of bits or bytes of information between the processes, sending and both receiving to do some functions between the processes. So that is what we know as interprocess communication. So in order to do that interprocess communication, there are several methods, not only the mode that we are discussing today, which is known as pipes, but also other modes, such as there are some message queues, semaphores, shared memory. So those things will be discussed in coming weeks. So today, the basic focus will be on this mode of interprocess communication, which is known as pipes. So before coming into pipes, we'll just have some background knowledge on kernel. So what is known as kernel, right? So kernel, I have also previously also given some very brief introduction to kernel. So here we will see it with respect to the processes, right? So kernel is called the core of an operating system. In other terms, the foundation layer. The function of the kernel is to communicate with hardware while managing the resources. So the computer has both a hardware and software resources. So those hardware and software resources should be managed, and that is done by the operating system. And for the operating system, kernel is the one responsible for specifically performing this task, right? So when we discuss about kernel, it does the functions such as process scheduling, process creation and termination. So process creation and termination, we learned last week how the process could be created uh, from a parent process, and then how it could be terminated. And so process scheduling is how, which process will function at a given time. The schedule for the process to operate or function, which process will be uh, processed or sent to the processor for performing a given task at a particular time. Such things are performed by the kernel. Not only that, especially the memory management. So we discussed about virtual memory last week. So this virtual memory, not only virtual memory, but the physical memory, both the virtual and physical memory, this mapping between the virtual and physical memory. So kernel is the one which is responsible for these functions. It has higher privileges than the user. So user is on top of kernel. So there can be different users for a given operating system or user groups. And usually those user groups have less privileges than the core of the operating system, it is the kernel. So what we discussed last week about the virtual memory, we discussed several segments of the virtual memory. The code segment initialized and uninitialized data segments, stack and heap. So those virtual memory or that address space is residing in user space, because most of the processors, this virtual memory is residing in the user space. So virtual memory is belonging to the user. That means one process could be run from a particular user, or another process could be run by another user. So those virtual memory will be residing in user space, but not in the kernel space. So we have two spaces known as kernel space and user space. User space is the private space for a given user. That is where this virtual memory concept is residing. And this mapping, I told you that that mapping is done by the page table, where the parts of the virtual memory is mapped to pages in physical memory. So this page table is stored in kernel because it is common. So kernel is a space which can be common for all users, but some users may even not have the access to kernel. Only a higher privileged user has the access to a kernel, like the root of an operating system, or in other terms, the administrator has access to the kernel. Right, so that is the background. So when we are doing inter-process communication, that means the communication between processors, so there are some different ways: pipes, semaphores, shared memory, message queues. So one or more of these techniques may get the help of the user space for communication. Some will get the help of the kernel space, right? So we have to look at, when we are discussing about each of the methods of interprocess communication, which of the methods use kernel space, which will use the user space. Some will use both the space for the interprocess communication, right? So now we will come to the first method of interprocess communication, which is called pipes, right? So pipe, so you can imagine about a pipe, water pipe. So the name pipe has come from the analogy to that of a water pipe. So if you get a water pipe, so I will just remind you this concept. So if you get a water pipe, you have two ends. You have two ends, where one end is the input end, where you insert the water, and the other end you can obtain the water. So here you have in, here you have out. So what is done from the inside is, we insert water from this side, and from the other side we obtain the water. So that is what done in a water pipe. Similar to that analogy, what is called this pipes in interprocess communication is nothing. So instead of water, we have bytes or data, which is flowing from this end to this end. So instead of water, in interprocess communication, we have data. Instead of insertion end, we have what we call the writing end. Writing end. So writing end is the end which we write data to this pipe, and the other side, output side, is called the reading end. It is the end which the processors read from the pipe. So you can see there is only one direction of flow for the pipe. There is only one direction of flow for the pipe. That means if you insert from this end, you should obtain from this end. So it is called a unidirectional byte stream, because you have one input and one output end. So you cannot use this side as the input and this side as the output. So it is unidirectional. That means data can only flow in one direction, right? So where this pipe is created is, if you create a pipe, that will be created and maintained in kernel memory or in kernel space, what we just discussed a moment ago. Kernel space, any process which has the access to kernel can access this pipe. Any process which has the access to the kernel can access this pipe. But the fact is, so this reading and writing end is identified using file descriptors, just like what we learned in lower level input output. So we should use one file descriptor to be used at the writing end and another file descriptor to be used at the reading end, right? And this pipe has some constant size, and that depends on the architecture. So for different operating systems using different computer architectures, so this pipe size will be different. Pipe size will be different. Clear this? Okay. So this pipe size will be different, and that file size can be this pipe size can be viewed using u limit or upper limit minus a command. So we will just visualize what is the pipe size in my machine. So I'll open the terminal and issue this command, upper limit minus a. So then you get the upper limit of different things in the operating system, where what is the maximum memory size, what is the maximum file size, what is the maximum data segment size, core file size, what is the maximum stack size, what is the maximum virtual memory size, and some don't have limitations, right? So for some things like virtual memory, you don't have a limit. So what we were interested was this pipe size. It says that we can have 512 byte pipes, eight number of 512 byte pipes. So that means we can have 4 kilobyte pipe. Pipe size is 4 kilobyte, but usually, even though this mentioned as 4 kilobyte, it is usually 65 kilobytes in Linux, these versions. And this is the one which is shown by ulimit, but it it usually is 65 kilobytes, but it is given here as 4 kilobytes. That doesn't matter. So what I want to emphasize is there is a limit for the pipe size, and the limit can be changed by programming. We are not going to see in here how we are going to change the pipe size. What we will be learning is how to write and read from a pipe and how we can use that for interprocess communication only. Okay. Right. So as I told you, it is programmable. How we can program? We can program using a function known as FCNTL. We can access that FCNTL function and set the pipe size, maximum file size that we want. What we are not going to discuss on that process. What we will be doing is we'll use these pipes for inter-process communications. So as I have explained before, it has two ends, the reading and writing ends. So I told you that we can use a file descriptor for the reading end and another file descriptor for the writing end. And the read and write can be done using this low level input output system calls. We have already learned these things, read and write. So in reading, what is done, it read from a file descriptor into a given memory of given size. What is done by the write system call is it write from a memory of a specific size to a file pointed out by a file descriptor. So we can use these to write and read from a pipe. So if you observe in pipe, you have the first in, first out, FIFO or FIFO, whatever, the architecture. That means what you wrote to the pipe in the first should come out from the read end of the pipe first. What you wrote to the pipe at last can be read from the pipe at last. So that is true even for the comparison with water. The water drop which was inserted to the pipe at first will come out from the other end at first. So you have first in, first out architecture. So once we write to the right end of a pipe using this write system call, the data will be immediately available to be read from the other end. But the fact is the file descriptors, even though the pipe resides in the kernel space, the file descriptors which is used for reading and writing, they have user space scope, or in other terms, it is called process scope. That means one process will have to use its own set of read and write file descriptors to access the pipe. Another process will have to use its own version of read and write file descriptors to access the pipe. So that is one of the important facts that you should keep reminded when you are discussing or learning about these pipes. So when we do a read operation, if we have less number of bytes in the pipe, it will read the currently available bytes in the pipe and block if the pipe is empty. But if the pipe is empty and if we are going to read from the pipe, then it will be blocked. That means not it will not allow us to read because the pipe is empty. So pipes can be used for inter-process communication. So that is what we are discussing. And another important fact, when we read that bytes that we read will not be any longer available in the pipe, just like water. When we get water out from the pipe, that water cannot be again taken out by another one. Like that one, when we read some information from the pipe, it is not longer available in the pipe. It will be no longer available in the pipe. So that is another important fact to remember about the pipes. So to create a pipe, we have this system called known as pipe. It is a very simple system call, but an important one, which is defined in this Unix Studio.h, right? And the name of the system task is pipe, and what will be returning is integer type, and what we should pass as the argument is a pointer to file descriptor array. So what will be passed as the argument here should be nothing but the read file descriptor and write file descriptor. Read file descriptor and write file descriptor, because the pipe has read end and write end. To write to the write end, you should have write file descriptor. To read from the read end of the pipe, you should have read file descriptor. So this is an array of size 2 of file descriptor. So this is simply an integer array of size 2 which contains 2 file descriptors for this pipe to be created. So this is called by some process. When a particular process calls this pipe system call, a pipe will be created in the kernel memory, and these 2 file descriptors will be connected to the pipe created in the kernel memory, but these file descriptors will have, as I told you before, the process scope. The process which created this file descriptor, this pipe, will have these file descriptors local to the process, but not in the kernel memory. Okay, so now we will go into describing this, what will be returned. So this pipe system call, when it is able to successfully create a pipe, it will return 0 on success, and when in error, that means when it is not able to create a pipe, it will return -1, right? So as I explained, it will create a pipe and allocate 2 file descriptors. So this is the argument which contains 2 file descriptors. So this file dis is a pointer of type integer pointing to an array of size 2, which contains the read end and write end. The first, so these are the 2. File des 0 is the first element of this array. File des 1 is the second element of this integer array of file descriptors. And file des 0, the first element, is connected to the read end of the file. So this file this 0, or the first element of this array of integers which is created in this process is connected to the read end of the pipe, and the other one, the second element, file des 1 of this array, is connected to the right end of the pipe. So whatever you pass here, the first element will be connected to the read end, the second element will be connected to the right end. So that is a norm. right? Whatever you have first will be connected to read, and another one, the second one will be to write it. So as I told you, this is having processor scope in user space, not in kernel memory. So, so when you call a fork for a process which has called a pipe, so when this pipe is called by a process, it will have two file descriptors connected with this pipe. And when you call fork, that means create a child process out of this process which has already created a pipe. What will happen is the pipe will not be duplicated because pipe is residing in kernel memory. So it will not be duplicated. But what will be duplicated is these file descriptors and new file descriptors local to each child process will be created when new child processes are created, and they will also be connected to the same pipe residing in the kernel memory. So the parent process has one set of file descriptors, and the child processes created out of that will have a different set of file descriptors. All will be connected to the pipe so that all processes can communicate with the pipe. Can communicate with the pipe. So whatever the number of processes which is connected with the pipe, it always has one direction of flowing and has read end and write end. Okay. So that is what I wanted to discuss on pipe. So that will be the background knowledge regarding the pipe. So you should have some understanding about this pipe system code. So when you create new child processes, the pipe will be shared, and the children will have different file descriptors connected to the pipe to communicate with the pipe, right? So that is the background. So I hope you understood the concept about pipes. So for your for more understanding, we will do some example exercises related to pipe. Then you will understand more, and it will refresh your knowledge on processors and virtual memory also by doing this exercise. So we'll begin that exercise. Okay, we'll do this first one first. So we are asked to create a pipe to transfer the message from parent process to a child process and display using terminal in the child process. So we are asked to create a pipe to transfer. So there are two processes. One is the parent process and child process. The parent wants to send the message, this one, message from parent process to the child process using a pipe. Using a pipe, and the child process should read this message and display that message in the terminal. Terminal means on the screen. In the child process, should print this message, and the communication should be done using a pipe, right? So we will create that inter-process communication. So there are two processes, child process and parent process. So the parent wants to communicate with the child and send that message. So what I do is I will change my directory to desktop and create a new directory and change directory into this one, and I will create a new file known as program.c and I will open it. Okay, for doing this task, you need to use the printf function. So you need to include stdio.h and the write and read system calls. Not only that, the pipe system calls, all of these are defined in Unix studio.h. So you need to include that. Then to handle errors, we need to include no dot h and as we are using some functions like exit function, we need to include stdlib.h. And then as we are using creation of child processes using fork, we have to use include sys types dot h. And as we want to use the wait system call for the parent process to wait until the child terminates, we need to use sys wait.h. Right, so those are the header files that we want to include, and we'll write the main program now. So the return type is integer main void and 0. Okay. So first, we are in the parent process. We have to create a pipe as the parent process. So the pipe system call, you saw that the return type is integer. Upon success, it will return 0. Upon failure, it will return -1. So first we will create a pipe. I'll say integer x, this pipe, and before that we have to create two file descriptors. So it is having the data type file descriptors, and the size is 2. So fd is a pointer to a file descriptor containing two integers. So fd0 and fd1. fd0 and fd1. So here, when we are declaring like this, it will create an array pointed by capital FD, and it will have two elements addressed by fd0 and fd1. So this will create two file descriptors, just an array of two integers. And if you can remember, what you have to pass here is the address pointing to this file descriptor array. address pointing to this file descriptor array. So this is the definition of pipe. So this is the address of file descriptor array, and this is return type. So address is nothing but capital FD. This is the address of this integer array. So what will this function does is it will create a pipe in kernel memory and associate these two file descriptors, which is the first one, fd0. fd0 is associated with read end of the pipe. And similarly, fd1 is associated with write end. Right. So if it is successfully able to create a pipe and associate these file descriptors, then it will return 0, otherwise it will return -1. So we have to check that one. So if x equal -1, then there will be an error. Else, if x equals 0, else if x equals 0, then that means there is no error. Then that means there is no error, you can continue. So but if x equal 1, we have to print the error. Printf, start with new line, pipe could not be created. We'll say pipe could not be created. Then print the error, and we'll say that it is associated with pipe. And print the error number. It is an integer. And then we will exit. Otherwise, we will print a success message telling, so this is parent process still. So we should distinguish whether we are printing from the parent or child. So that's why I'm specifying this as parent. Pipe created successfully. And after creation of pipe, now the pipe is successfully created, then we have to create a child process. So that one we are going to do it using the fork. So last week we discussed on the fork system call. The return type is a process identifier, PIDT. Data type is PIDT, process identifier defined in this systypes.h. And we'll declare a variable capital PID standing for process identifier and call system call fork, and it has no arguments. What it will does is it will create a child process and return the process ID. So we discussed what will be this process ID. If this process ID is -1, then that means there is an error. If it is 0, then that means it is the child, and if it is greater than 0, then it is means this is the parent. For the parent, it will retrieve the process ID of the child. Process ID of the child is a positive integer. For the child, it will always return 0 value as the process ID. So for this one, I will use a switch statement. Switch based on the process identified. So there are three cases. Is case -1, that is the error. Case -1, we had to some task. In the syntax, we have the break. And in case 0, that is the child. So here you have, this is error. And this is child. Child process. And last one, we have the parent process. So any other integer other than this one will be the parent process, which is, we will get using the default. Right. Okay, this will switch based on each case. So in this case, we have to print this kind of thing. So here not the pipe, we'll say process. Process could not be created, so the error is related to process, and print the error number and exit. Okay, then as the child process and as the parent process, this is parent process. So what did the question say was, we have to first write from the parent process some message called message from parent. And I told you in the creating this fork, this child is after this fork calling, this it is not known whether this child or the parent will run first. So that means both of them will run parallelly. So until until we want the parent to print that message from parent, we want to suspend the child. So I will suspend the child using the sleep function. I will suspend the child for 100 microseconds. So this is coming in seconds. 0.0001 means 100 microseconds. Child will be suspended for 100 microseconds. Within that time, the parent should write to the pipe. Parent should write to the pipe. So how to write to the pipe? First, it should create the message. So message is nothing but a set of characters. I'll say MSG 1 of size 20. It is enough to store this message. Message from parent. This is the message from parent, and this should be written to the pipe. How to write to the pipe? That is important. That is simply done using the write system call. So you know how to use the write system call by this time. So the return type is integer, I create a variable called bytes written is assigned write. Write to which file descriptor? So the pipe is associated with two file descriptors, FD0 and FD1. 0 is associated with read end, 1 is associated with write end. So we have to write to the right end of the file using the right file descriptor. What we want to write is this pointer, and you can remember that this is of type void pointer. So you have to cast to void pointer, which is this msg1 is a character pointer, msg1 comma, then the size of this one, size of msg1, and this may be success or not. If this is -1, then write into pipe is a failure. If it is not equal to -1, then that means the write into pipe has been successful. So we have to check and print that one. So if bytes written is equal to -1, we have to do something, otherwise we have to continue. So if this is the case, we have to print the error. And this time, so we have to tell which process are we. So this is the parent process. So we'll just say parent. So what it couldn't do, write into pipe failed. So this is writing. So I'll just say that it is the error is related to writing, and the error number is this one, and still it is from parent. Right. So this is if the error occurs. If the error does not occur, then we should print. We should specify that we are from parent. The process is parent. Parent says that return to pipe successfully. Return to pipe successfully. And then what should be done? Parent will write to the pipe, then it should wait until the child retrieves that one, and then child print that the child has received this message, and the child will terminate. So after this one, the parent should wait until the child is terminated. So how do we do that? So you can remember this system call, wait for process ID, wait PID. This thing we learned last. So if you don't remember, I'll just remind you what this is. Right, so this is a system call that I'm going to use here. So wait for process ID. So the first system call is the process ID of the child that we are going to wait, then status and options. So about the status, I told you last week that if the state of a child process can change by a signal also, the child could be stopped and then started. So those are also state changes of the child process. But in this lesson, we are not interested about them. We are only interested about that whether the child is terminated or not. That means there are only two status. So in that case, we can keep this status null, specifying that we are only interested in the termination of the child, not any other status, and these options can be kept for 0. That means there are no any other option. We are only interested in the termination. And if we pass the process ID of the child, the exact process ID of the child, then the parent will wait until that particular child is terminated. And if we pass -1 as the argument here, then if the parent process has multiple children, it will wait until any of its child is terminated. Until any of its child is terminated, the first child terminates, this will return. Right? So that is the how this is used. So here there is only one child. If we want, we can use -1, or just we can use this process ID. Why? This PID is the one which is retrieved here. Process ID of the child is retrieved for the parent process in a fork system call. So if we pass this process ID, then that means this is the process ID of the child. And we are not interested in any other status, so it is null and options are 0. This will wait until the child terminates. Then the parent will exit by printing a statement. I'll say just parent exiting. Parent is going to exit. Right, so that is in point of view of the parent. So now we have to tackle with the child. So when this child is cleared, it will first suspend its process and wait and give time for the parent to do this task. So parent will write this message to the pipe and print this written to pipe successfully, and it will come and wait here. Wait until the child terminates. Then after this time expires, then the child should read from the pipe. So as this is a child of this parent, it is having access to these file descriptors, but not exactly this file descriptor. This file descriptor is local to the parent process, but the child also having two file descriptors with the same name, but it is local to the child process. A copy of this. So this was told in last week. So this is local to a file. So this is residing in stack. This is local to a file. So this is residing in stack. This is not a static variable or a global variable, but this is a local integer variable. So this is residing in stack. So the in the virtual memory of the parent, these two file descriptors are there. When fork is called, a copy of these two file descriptors will also be available in the child also. So that means we can use those two local file descriptors in the stack of the child to have access to the pipe. because these two local copies of the child file descriptors are also connected with the pipe, because we have previously the parent has connection with this pipe, these two file descriptors. So in the child also, that child's own version of those two file descriptors are connected with the common pipe. Okay. So first I will create an empty variable or a buffer to store the red set of bytes, red string. So msg I'll say 2. So this is a string array which is empty. So what I'm going to do is I'm going to fill this empty array with what is read from the pipe. So by this time, pipe has been written by the parent with this message using this command. So by using this command, the parent has written to the pipe. That means this message from parent is there now inside the pipe. So what we are going to do is read from the pipe. So what we are going to do is, so we have to do the error handling also here also, integer bytes read. So we have to use the low level system input output function read, and now the file descriptor associated with the read end of the file is fd file descriptor 0. And we are reading into this buffer, and it should be casted to void pointer msg2, and here it is size of msg2, size of this message. So now this will read to this buffer, and we should check whether an error has occurred or not. So we have to check if bytes read equal -1, we have to print the error. Otherwise, we will continue. To save time, I'll just copy paste this one here. And this time it is not the parent, it is child. And this is reading. Child says that if an error occurs like this, reading from pipe fail. Child, and the error is related to reading, an error number, and then exit. Then if it is successful, then that means this has successful read. So we will have to print that turn. So this is child read from the pipe successfully. So after reading from the pipe successfully, we are asked to print that turn, I think, to the child and display using the terminal in the child process. So we have to print it on the terminal. So now we are in child process, we have to print it on the terminal. Printf will say the message received is. So message received is read from the pipe and stored in this buffer pointed out by this MSG2 character pointer. So if we read what is now there in this buffer, then we read what was written from the parent. So we will read what is there in this message MSG2. So it is an character array string MSG2. And we will do this one and we'll print that now we are going to exit. Child is going to exit. Here I should say that this message is from child. Exiting. To acknowledge that it is going to exit and then exit. So the child will read the message and then print the message and says that it exit and exit. After that, the parent process, which is waiting until the child is exiting, will get this one returned. That means it will get a success message, or so whatever which is returned from the wait PID. Here, PID T. So what will be returned is the process ID of the child. So PID T. So process ID of the child will be retrieved. So upon that one, when a value is returned, then this function will be called. Right? It will be over. Then it will execute the next line. Until the state of this one is changed, it is not there. So if it is an error, it will immediately return -1 upon error. So we are not going to check the value there. But if we want, we can check the value also here. Right. Okay, we'll check the value. PID T. We'll say process ID 1. So if it is in error, we will print an error, otherwise we will print this message. If PID 1 equal -1, we'll say something like waiting failed. Waiting failed. This is waiting. Right, so that is the case, and this should be done otherwise. Else. Else we say that so we'll say that child also exited. Parent will tell that. So if the waiting is successful, the parent will tell that child exited. And parent now is exiting, then exit. Parent will exit. So this is the program which was expected to be written. We'll see whether this is compiling or not. as it was compiled, and we'll run this program. Okay, we get these success messages. So parent says that, so what will be executing first? It is the parent, because we have in the initially when we call for child is suspended for 100 microseconds. So parent says that pipe cleared successfully. It is printed twice. I don't know what the reason is. Then child says that read from pipe successfully. Wait, I think I have when we write to the parent. So this is not there. Parent written to pipe successfully should be there first. This should be written to pipe successful. This Linux console is sometimes giving different results. So I think this is what is shown as the second one. So this should be written to pipe successful. It is also coming as pipe created successful. So this should be written to pipe successfully. Then child read from the pipe successfully. Then child prints this message, which was read. The message received is message from parent. Child says the message received is, this is the one which was read from the pipe. The child just read this from the pipe. Then it will say that child say that it will exiting. Then parent, this is coming here. So this should be here. This is sometimes it is this due to indentation it comes. So however this should come here. Then at last parent says that the child exited. Then the parent will exit. Parent will exit. Right, so that is the process. So this proves that by here, child, message has been received by the child from the pipe. Otherwise, this will not be printed. This is printed from this MSG2 buffer in the child. Here it is reading from the pipe into this MSG2 buffer. Then here it is writing the content of MSG2 buffer. If the parent has not written it there, this will not be able to read. So due to something, these things are showing in a different order in this console. But if you wrote this to a file, it will be correctly shown. It will be correctly shown in this order. But this proves that the child has received it, then the child exit, and then the parent exit. So the order is there, but some things are not showing in the correct order. Some things are duplicated, like here. Something some fault should be there in this terminal. But the logic of the program is correct. Okay, so we created a pipe, then we wrote a message from the parent, we suspend the child and wrote a message from the parent. Then the child read that from the pipe, and it printed and exited. Then the parent waited until that child terminated, and then it also exited. Possibly that error could be there because of this waiting time is not long. We'll see. No, still it is there. The order which is showing is not correct, but the logic is correct. Right. So we will move on to the next example. So here there is only one direction of communication established in this example one. The message is sent from parent to child only. But in the second example, we are asked to create a bidirectional communication channel using pipes to transfer the message from parent process to the child, and then the response message, response from the child process to the parent process, and display using terminal in the parent process here. So additionally we are asked to get the response from the child. But we cannot use the pipe to create a bidirectional. The pipe will, inside the pipe it will not be bidirectional, but using the file descriptors associated with the pipe, we can establish bidirectional communication. So we will just change this logic of the program and obtain that second program. So we have almost written half of the second program also. That means we have written, that means sent the message from the parent to the child. We have written the message from parent to the child. Okay, so in parent, this is the first process. Okay, it is done. In the child, it is suspended. Okay, it is the same here. Then it will read this set of bytes. Then it will not exit here. Then we have to continue. The message is received. Message received is this one. Then it will have to now write to the buffer the response. So we have to create a response. I'll say that it is character message 3. We say it as response from child. So this is the response from child. So it read from the pipe first. Upon successful reading, now it is going to create a response and send to the pipe to be read by the parent. So it created a response, then it should write to the pipe. So I'll use the write. So I'll say integer bytes written. But I use byte written here in the parent process. So should I use a different variable, or can I use the same variable here? That is a problem. I can use the same variable name here because this byte written was created. This is local to the parent process, and this is local to the child process. So even if I give this same name, there is no collision between these two. There is no collision because this is in one process and this is in another process. So I'm going to write to the pipe. So I can use the same file descriptor. File descriptor 1. But this is in a child process. Child processes file descriptor 1. Writing end of the pipe connected with FD1 of child. Till write to the pipe what is there in pointed by MSG3. And we have to check the errors. And to check the errors, I will just, to save time, I will just copy paste this one. So if bytes written is -1, then we have to do that one. Otherwise, we have to check. So this is not parent. This is child. Child says if this is -1, then that is error. Write into pipe fail. But previously it was the parent which said, now it is child. Otherwise, child should say written to pipe successful. And here it will not wait for a process ID. After writing to the pipe this message response, child will exit. Child will exit. Child is exit, then the child process will terminate after this one. So the parent process, it first writes this message from parent, and upon success, parent. So upon success, parent will say that written to pipe successfully. Then wait until the child process is terminated. Child process will be terminated here. After that one, after that, if it is successfully, this PID, I mean, if the parent child process is successfully terminated, it will say that the child exited, and then it should not exit, but it should now read from the pipe. Now it should read from the pipe, right? It should read from the pipe. So I say, so previously here it is bytes written, so we don't have any other variable local to this process in name bytes read. So I can use integer bytes read. We have a variable with same name, but it is having the process scope of the child. It is not, this byte threads does not interfere with this byte thread. So this byte thread, so here we will read from the pipe, and we should have some empty buffer pointing to be read. So I'll use that one as character SG4 of size 20, which is empty, and reading is done from file descriptor index 0, and read to this empty buffer, and at last you have to pass the size of this buffer. And we have to check whether this reading is successful or not. And here, so we have to check whether if bytes read equal -1, we have to print the error. Otherwise, we have to continue. So first we will print the error. So this is parent, this is not waiting, but this is reading from pipe. So here it should say that the parent should say reading from pipe fail. And parent, this is reading an error number and exit. And upon success, if reading is successful, it should print this line, parent. Then it should print the message it read. Okay, first we'll say that successfully read from pipe. Then we'll print the message read. So parent should say message read is what is contained in the character pointer pointed out by this MSC4. Because MSC4, this character pointer stored what is read from the pipe in there. Read is what is contained in MSG4. Then it will say that parent will say that exiting and it will exit. So this is the program for enabling bidirectional communication between the parent and process using pipes. So if I simply explain what does happen, so in the parent, so it will create a message from parent and write so it will write that message to the pipe, then it will wait until the child terminates. It will print this successman, it will wait until the child terminates. If child terminates successfully, then it will read what is now there in the pipe. What is now there in the pipe is what has been written by the child. Child has written the response message to the pipe by this moment. So it will read that content and print. So what does the child does is it will wait initially until the parent writes the message from parent, then it will read the content of the pipe. Then after this time the pipe will be empty. Then it will print what is read from the pipe into the console. The message child says that message this one, and it will create a response message and write that to the pipe, and it will print a success message and then exit. So this is what happens. So we'll see whether this one is successfully compiled or not. Here there is a missing else. This work is here. I think now it is okay. Okay, so we'll okay. The parent says that the pipe cleared successfully. It is coming twice again. Okay, child says that read from the pipe successfully. Okay, this prints the message from parent. Child print. Then it has written to the pipe. It has written to the pipe. Child had written to the pipe. Then child had exited. Child had written to the pipe and child exited. Then parent had successfully read from the pipe. Then the message read is response from child. So this confirms that the parent has read from the pipe the message sent from the child. Parent process has read the message sent from the child, which is response from child, and parent exit. So this has enabled the bidirectional communication between two processes, parent process and child process. So this is what you call as inter-process communication. So using pipes, we have enabled the inter-process communication. So this is bidirectional. Previously it was unidirectional. But still, even though this is bidirectional communication, the data communication direction through the pipe is still unidirectional. Within the pipe, data is traveling in one direction, but using the file descriptors associated with the pipe, we use those to enable a bidirectional communication channel. Even though the pipe is unidirectional, still here also the pipe is unidirectional, but using the file description, we manipulated it to using the read end and write end. We use as if it were a bidirectional communication channel. Right, so that is what we have to discuss on pipes. Right, so that's it. So we will move on to the second method of inter-process communication called message queues. This one. So that is another way of enabling inter-process communication, or in simply IPC. So we can use this command. So we'll just issue this command in Linux terminal and see what we can observe. IPCS -L. Command not found. Yes, it is not capital, it is simple. IPCS -L. So it says that message limits. So this is for message queues. So this shows limits for three types of interprocess communications. This is for message queues. This is for shared memory. This is for semaphore. Shared memory and semaphores we'll discuss in coming lectures. So what we are going to discuss today is what we call as message queue. So this specifies the message queue limits, maximum size of message, 8192. Maximum queue system wide, default maximum size of queue. 16,384 bytes. So likewise, even in pipes, as I told you, we have a limit. If we exceed the limit, we will not be able to write to the pipe. So likewise, so in this message queues or in other any method of interprocess communication, we have limits. So you can visualize these limits using this command, interprocess communications minus L list. Okay. So we will see what this message queue is. So we'll in this week we'll have a theoretical background on message queues, and in next week we'll begin the practical exercises of the message queues. Right. So this message queues, the concept is similar to pipes, but there are some differences between message queues and pipes. So this is one of the main difference. So it is stored as a linked list. The data structure used to store a message queue is a linked list. Linked list. The data structure it was used to store a pipe. It was a FIFO buffer. Pipe is nothing but a FIFO buffer. What is coming at the first should go first, right first. But there is nothing like in message queues. It is, if we want it, we can use it as FIFO, but if we want, we can read from anywhere in the linked list. So message queue is a linked list. The data structure is a linked list stored in kernel space. The pipe is also stored in kernel space, not in user space. Likewise, the message queue is also stored in kernel space, but a different data structure is using linked list. Okay, first as we learned about pipes, we'll have some comparison between message queues and pipes. So in pipes, we had file descriptors. So I told you that those file descriptors associated with pipes have the process scope or they are in user scope. The user and process scope are similar. But in message queues, so the file descriptor was used to access the pipes. So how the message queues are accessed is by using something known as message queue identifier. Message queue identifier, and those message queue identifiers, they are not having process scope, but they are having a kernel scope, right? So they are residing, so those are residing in the kernel. What is called this message queue identifiers are having the kernel scope but not the process scope, so any process can access it. So if you compare it with the pipes, the file descriptor associated with the file, I mean the pipe has two file descriptors, and those file descriptors were local to the each process. You saw that in the previous demonstration. The child process had a set of file descriptors, its own version, and the parent process had its own version of file descriptors which used to access the pipe. But in message queues, it is different. The message queue identifier is common between the processes, so it does not have process scope. And there's another difference. So these messages to the message queues are written in units or called message queue message structure. There is a message structure to be written into a message queue, so that we have to write in whole of that structure or receive whole of that structure. That means remove that whole of that structure. We cannot remove part of that message or read, insert part of that message or read part of that message. But in pipes, we could extract by changing the third argument of read. We can extract different number of bytes, even part of a message, by changing the size parameter. If we write 20 bytes to the pipe, we can easily retrieve 10 bytes from the pipe by keeping the remaining 10 bytes within the pipe and removing the first 10 bytes written. But we cannot do that in message queues. We have to read and write as a whole message. And the other difference is the message queues can be read as, I told you this point already, FIFO or retrieved by using the integer type, the message type. So so if there are set of messages, say 5 messages in a message queue, you can identify this 5 messages by using the message type. So in a message, you have the message text and message type. Like here, I will come to this point here. This is the structure of a message in message queue. So you have message type and message text. Using the message type, you can retrieve the message that you want without retrieving the message, I mean, from the queue in a first in, first out manner. If you want, you can use the first in, first out manner. Otherwise, you can read using the message type. You can read using the message type. So that is another difference between the message queues and pipes. Okay, now we come to the structure of the message. So in pipes, there was no structure. We can write any number of bytes, we can read any number of bytes. But in message queues, we should define the message in a structure. So it is declared with this structure. So structures we had discussed when we were discussing about C programming. So we can create a structure called message. So identify this message. And so it has 2 attributes or 2 variables. The first one is long type variable called message type. This is used to identify the type of the message in the message queue. So to a group of messages can have one message type. Another set of messages can have another message type. And then the body. This is the actual data of the message. It is a string array or a byte array. This is the byte array. This is the content of the message, and it is identified using as a group by message type. So this is the structure of a message which is stored and retrieved in a message queue. Okay. So just like pipes, we have to study several system calls when we are referring to the message queues also. Right? So the first one is the FTOC. This is an abbreviation for file token. This is some kind of a token given for a file. Sometimes kind of a token given for a file. So this is used to create a key or a token for a given file. Okay, so this is defined in sys IPC.h and systypes.h. Systypes.h is needed to include because the return type is key T. key T, and F dot file token. So we need to include sys IPC.h. So sys stands for, so there are two uh, realizations of interprocess communication. One is called the System 5 architecture and the other is called the POSIX architecture. System 5 architecture and POSIX architecture. So what we will be discussing in this class is System 5 architecture. So there's no time to discuss on both architectures. There are similar functions are there in POSIX and System 5 architectures. Similar functions are there, but the arguments and the functions name are slightly different. So these are just two realizations to do the same task done. So there is no meaning in learning both of them. It is enough to learn only one out of them. So I selected System 5 architecture to be taught to you. Right? So here the return type is key T. So key T is a System 5 IPC key, interprocess communication key, uh, which is a unique key given for a given file name and a given, this argument is called project ID. Project ID. That means for the given, for the same given file name, you can have different keys by changing this argument project ID. Okay, upon success of this FTOC system call, a valid key, a unique key of data type key T will be returned. Otherwise, just like other system calls, -1 is returned upon failure. This FTOC file token. Okay, so as I told you, even if you issue the same file name, you can use different project IDs. This project ID stands for project ID. So you can use this integer, valid integer range is 1 to 255. That means 8 bits of integer. Least significant 8 bits of the integer is 1 to 255. You can use as the project ID to get 255 different keys for the same file name. So as I had told you, it is can take value from 1 to 255. So what does this FTOC does is it generates the system 5 key for the file name specified this with the project ID. So why we are generating this key, you will understand in a moment. Why we use this key generation, you will understand in a moment. So that is to use this in this system called MSG get, message get. So this is you need to include this is types.h and sys IPC.h. So this is sys stands for system 5. IPC stands for interprocess communication. So system 5, if you are using system 5 IPC, you need to include this header, system 5 IPC. And this particular thing, as we are using message queues, if you are using message queues, you need to include this header, system 5. Message queues are defined in this header. I mean, message queue system calls, I mean, those functions are defined in sysmsg.h. So this, if you want to use this msg get, you need to include this header file. So what does this do? It is used to create a message queue if it does not exist. So the best analogy is the open system call. So you learned about this open system call when you learned about low level file input and output. This open. So what does this do is it will open a empty file descriptor and associate a file with that one, right? So just like that one. So if the file to be opened does not exist, if we have given the arguments or create, it will create the file if it does not exist. Just like that time, we can use this MSG get also to create the message queue if it does not exist, and return the message queue identifier. Message queue identifier if it does exist. So what does this do is it is creating or returning the message queue identifier as an integer. So what is returned from this MSG get is important. So what is passed as the key is what we generated from file token or this IPC key, system file IPC key. You can generate the system file IPC key either by using this ftoc, using this, or you can just say that you are going to create a unique message queue. That means this key, a unique key is passed here. Then you can use IPC private. So as the key argument of this MSG get, either you can use a key generated like this using the file token or if token command, or you can just pass the argument IPC private here as the first argument of MSG get, message get. And second argument is message flag. Message flag. So just like in the open system call you had or create, truncate, so, or append, like those things. Here also you have such flags. So IPC create is to specify that if the file does not exist, create. And IPC EXCL exclusive states that it is exclusively for creating. So I have described here, it is used only for creation. That means if the message queue, if this key is associated with some message queue identifier, it will not retrieve the message queue identifier. That means it will not return the message queue identifier of an already existing message queue, but it is exclusively for creating. If this key is already associated with the message queue, then it will return an error if you have specified the IPC exclusive argument. And you can owe that with the user the privileges for this message queue. You can specify the privileges. You can specify the read privilege for user or write privilege for user, like, or you can just owe this with 0666. This will set read, write, and execute privilege for all type of users. 0666 instead of these things. So because this is an integer, right? So if you specify 0, then it says that it is not for creation. It is not for creation. And 666, it is the all read, write, execute privileges for all users. Either can be used this or this. So I have said that IPC create is similar to OCreate. So only the change is O has been replaced by IPC. IPC exclusive I already explained that it is only for creation. If this key is associated with a previously created message queue, it will return -1. That means error. And how to retrieve the message queue identifier of an existing IPC. So for that one, we have to specify this key as not IPC either, IPC private. If we specify IPC private, then we will never be able to obtain the message queue identifier of an already existing message queue. So we should not have this IPC private, and the message flag is 0. Message flag is 0. That means none of these are there. IPC create and IPC exclusive are not there. Message first flag is 0. 0. Then we can get, if you have message flag as 0 and this one as not IPC, then that means a key. For example, a key generated by f-talk. So the advantage of f-talk means using f-talk you can store what this key in a variable. Using f-talk you can store this key in a variable, and later you can obtain the message queue identifier using this message MSG get. If you specified IPC private, then you will not be able to get the message queue identifier of a previously established queue. You can obtain the message queue identifier of the creating message queue using this one, but not a previously created one. If you want to get the message queue identifier of a previously created message queue, you should not pass the key as the message IPC private. Then you should pass the key related with the previously created message queue that you created using f-talk here. Then this message flag should be 0. Then you will be able to retrieve the message queue identifier using this MS message get. Right. So that is about message get. So what is the function of this message get? To create a message queue. If it does not exist, if it exists, it will retrieve the message queue identifier of the already existing message. The function of f-talk is creating a IPC5 key to be used in creation of the message queue. Right. So we studied two functions or two system calls related to message queues. And the next one that we will be studying is MSG send, message send. So the same set of header files you have to include systypes.h, ipc.h, message.h. And this has 4 arguments. This has 4 arguments. And the return type is integer. So the function of this message send is to send a message specified by this message size. This is the size of the message and pointed out by this message pointer. And this message pointer points to a message structure of a message queue. So what is a message structure? This one. So a message can be created using this message structure, and the second argument of this MSG send points to such a message created, and the first argument is the message queue ID. So how to retrieve the message queue ID? Message queue ID can be retrieved at the creation of the message queue or later, as I described before, using this MSG get. You can obtain the message queue identifier using MSG get. That can be used as the first argument, then the address of the message that you want to send, then the size of the message you have to send, then at last additional message flag which specify the behavior of how to send it, how you want to send. This sends to an existing message queue, then identified by using this one. So upon success, this will return 0 and upon success, yes, this will return 0, and upon error, this will retrieve or return -1. Right, so we have some more discuss on MSG send, and we'll stop for today by discussing this one. So just like pipes, if the message queue is full, you cannot send a message to a already full message queue. Or if the message queue is going to be filled just by using by sending the particular message, if it is going to be filled over the limit, then this message sent will fail and it will return -1. And we'll now discuss about what is to be passed as the MSG flag. MSG flags, right? So what is passed as the MSG flag? What is specified in this one is it will specify whether it blocks or not if the message queue is full. So I told you about the default behavior. So default behavior is if the message queue is full, it will block. And you can optionally change that behavior using the argument by passing here IPC no wait. So what is this IPC no wait is simply an integer. So we don't know what is the value of this integer, but it is defining those header files, this msc.h, these things. If you pass IPC no wait, so it will not block even if the message queue is going to be full. It will not block. It will attempt to fill up to the limit it can, then till fail. Then it will fail. And the default behavior is specified by the integer 0. If you pass 0 here, then if the message queue is full, it will block. If you pass 0, right? If it will block, if that will block mean it will not allow for this message to be passed to the message queue. So those are the things that we have to discuss today. So we first today started by discussing on pipes and the kernel. Then I demonstrated several examples of the pipes. Then we came to the second method of interprocess communication using message queues, and I gave you an introduction to message queues. First, I compared the pipes with message queues, and then went into the structure of a message queue, then went into several system calls that we can use in the system 5 message queue when implementing ftalk, msg get to create a message queue or to get a message queue identifier of an already existing message queue. Then to send the message, we have to use message send, msg send. So next week we'll be discussing the remaining functions, and we'll go to the exercises of message queues.